Hello, let's go over lesson 2, how stars shine today. So the first section we went over characteristics of stars. We talked a lot about the different types of spectrums. And we mentioned what color means, that the more red a star is, the cooler it is, and the more blue, the hotter it is. And we looked at the HR diagram. Now we're going to see how they form and how they shine. So first up, let's get a definition down. A nebula is a large cloud of gas and dust in space where stars are formed. All right? The space between stars is called interstellar space and contains mostly gas and dust at very low densities. So nebulas are where there's a lot of gas that make essentially a cloud, and interstellar space is almost nothing. Interstellar space is really, really thin gas, whereas a nebula is there's a lot more gas there, a lot more gas and dust in a nebula, not nearly as much in interstellar space. It's very low density. What you see here is a picture of essentially a cloud of gas and dust. It's blocking the light of all the stars behind it. So you see a bunch of shiny things and then there's a dark spot. It's not that there's no stars there, it's that there's a cloud in the way of where we're looking. And that cloud is blocking all the light from behind it. But this is what some nebulas look like. Some are really pretty and some are just blobs of darkness. Speaking of the really pretty ones. Now we learned about the different spectrum, and the reason why we learned the different spectrums earlier, so we know what we're talking about here. An absorption nebula blocks light from stars contained within the nebula. So there might be stars inside of that gigantic cloud of gas and dust, but we can't see it because it's absorbing the light. We also have things called emission nebulas, which emit light when they are excited by energy from stars within the nebula. So absorption, remember, those are just absorbing light. These emission nebulas are absorbing those specific colors and then re-emitting those specific colors. So the reason why this gas is like pink and blue in here and stuff is because the atoms that they're made of are getting hit by this starlight, absorbing certain colors, and then that gas is releasing those colors back out. So that's why we get these different layers of gas, because this dust and gas must be made up of something different than this blue part. I think this picture is so cool. It looks like an eyeball. It's really cool. So so how do stars form? Well, the gravitational force between particles and dust clouds can cause clumps of matter to form and heat up in a nebula. So if you have, remember, interstellar space doesn't have much stuff, but the nebulas have a lot. So it's possible that in the nebula, some of the little gas particles and the dust particles meet and they get a little bigger. And because they're a little bigger, they get a little bit more gravity, which means they can grab a little bit bigger particles away from them. And then once it gets those, it gets even bigger and can grab particles even farther away. So it just keeps building up like this until eventually it gets enough stuff to start squeezing itself so hard that it heats up. Okay? It's not undergoing any nuclear reactions. It's just squeezing itself so hard that it's starting to heat up and become bright. And this is what we call a protostar. So that's just a ball of gas and dust that is squeezing itself so hard it is bright. Not technically a star, it's a protostar. It's going to become a star. Here's some pictures. Ooh, excuse me. Actual pictures and then artist concept of what protostars might look like. We see that there's a center here, and then all this gas and dust is kind of being drawn into it. All this gas and dust is being drawn into the star thanks to gravity. Some of it might get launched off the side of it, but it's trying to collect enough material. It's not a star yet. It's just bright because it's squeezing itself so hard that it's heating up. When the temperature of one of these protostars becomes high enough, though, something called nuclear fusion occurs. Nuclear fusion, when that occurs, that's when it's considered like a star. So right now, our sun is undergoing nuclear fusion in its core. That's what makes it a star. A protostar does not have that nuclear fusion, but once the protostar gets hot enough from squeezing itself so hard, it can start that process and it can become a star. And it's important to realize that nuclear fusion is when that happens. And eventually that energy from the center of the sun, from those nuclear reactions, get to the surface of the sun, which we know is called the photosphere. And the photosphere of any star, not just our sun, but the photosphere of any star, is the one responsible for emitting electromagnetic waves in the form of visible light. Oh my gosh. It's like the second time I've yawned. In a nuclear fusion reaction, two smaller nuclei combine to form more massive, larger nucleus. To form a more massive, larger nucleus. So that's what's happening in the inside of our sun right now. That's what is happening on the inside of any star right now. Two small atoms are combining to form one bigger one. We spent the majority of the year learning that that can't happen, because in chemistry you can't combine two atoms, right? If you have a water molecule, it's H2O. It's two hydrogens and one oxygen, and they're all next to each other, but they don't actually combine. In nuclear chemistry, in these nuclear reactions, you can have two hydrogen atoms actually smush together and become one helium atom. Oh, sorry, I skipped that last part. So not only is the photosphere giving off visible light, it's also giving off infrared waves. And you see it says most of the energy emitted into space is in the form of visible light and infrared rays. Infrared is a type of electromagnetic radiation that we cannot see. We can make devices that can see it, but our eyeballs cannot see infrared waves. If you could see infrared waves, then you could see the, if you have a remote control and you ever point it towards the TV, that thing is shooting infrared rays. So if you could see infrared, you'd be able to see the signal from your remote hit your TV. So here's the fancy process that's happening inside of our sun and in a lot of other stars out there that's making enough energy to essentially power the star. Remember I talked about combining two hydrogen? Well, let's just look at this part up here, this one little box that I'm kind of highlighting, one little area. These protons are hydrogen nuclei. And if you get two hydrogen nuclei to run into each other fast enough, they can combine and form another type of hydrogen. This only happens when it's really hot and really squished, like in the center of the sun. So these are breaking all the rules that we learned about chemistry earlier in the year, because this is nuclear chemistry. So these two protons smush into each other and they become this other type of hydrogen. And you see that a positron flies off. Well, a positron is a positive electron. Remember we talked about electrons a long time ago. Electrons are super tiny, but they're negative. These are super tiny, but they're positive. Again, nothing you guys have ever come in contact with has ever had a positron in it. It only happens in these crazy nuclear reactions in the center of planets and stuff like that. So two protons smush together, they make one other weird hydrogen, and they shoot off one of these weird positron particles. This happens twice. Okay? One of these other hydrogens smushes into a normal hydrogen, and the same kind of deal happens. Once this proton squeezes with this proton and neutron, they actually combine in total to make a helium. And this happens over here as well, because this happens twice. So now we have two helium isotopes, which means, if you remember, there's different types of helium. It has a different amount of neutrons. Well, if two of these heliums squish together, they both kind of throw off one of their protons, and it becomes a helium nucleus. And then this helium nucleus kind of sits in the center of the sun, heating up, but not really doing anything. So every time one of these protons smacks into each other, they release a bunch of energy. And anytime this hydrogen smacks into this weird hydrogen, more energy is released. And anytime this helium isotope smashes into another helium isotope, more energy is released. And each time this energy is released, the energy eventually makes its way out to the surface of the sun, and that energy eventually lights up the Earth, lights up the planets, goes out into space in every direction. But it all comes down to this crazy chain of reactions happening on the very inside of the sun. Okay? Now let's think about the star trying to hold itself up. So we know gravity squishes things, right? So then the question might be, how come a star just doesn't squish itself if it has so much material? And the answer to that is that every time you fuse, every time you do one of these, you're releasing energy, right? Well, releasing energy makes an outward force that counteracts the inward pull of gravity. So a star is trying to squish itself, but the explosions on the inside from all those nuclear reactions are pushing the star out. And when the outward force produced by the fusion balances the inward force of gravity, stars stop contracting, meaning stars stop squeezing themselves. So our sun is constantly trying to squeeze itself, but it's also having a bunch of energy blow up from the inside, which means it eventually balances out to the size and shape that it has now. If for some reason the inside of our star, inside of the sun, starts to increase the reactions, it'll get a lot more hotter, it'll get a lot more explosions, which means the explosions will be stronger than the gravity, and the explosions will make our sun bigger. And that's what this last note is saying. So here we see all the red lines from the explosions and all the blue lines from gravity are equal. I meant to say even. Are equal. But what can happen if the core of the sun, for whatever reason, starts having more and more reactions, then the explosion pressure is going to be stronger than gravity, so the star is going to get bigger. And on the other side, if the reactions slow down in the center of our sun, then gravity is stronger than the explosion pressure, and the star shrinks. There's a lot more complicated relationships here, but this is all we need to know for this class. So stable forces determine whether a star expands or contracts. Remember, the nuclear reactions determine if it expands, and gravity determines if it contracts. So we know where the stars get their light from. They get from the nuclear reactions on the inside. We know why stars aren't expanding forever or squeezing down into nothing, because the explosions and the squeezing balance each other out. But remember when I was talking about when the hydrogens combine and make that helium, the helium just kind of ends up in the center of the star. And in a lot of cases, the helium either doesn't get used or it kind of gets used up as fuel. So it's possible that some stars, not our sun, but some stars can get that helium and do almost the same process and squeeze helium together and make a bigger element. And then take that element and squeeze it together and make a bigger element. So fusion continues in a star until all of the gases inside the star have combined to form heavier elements. The bigger the star is, the heavier elements it gets to make. Our star is not that big, the sun is not that big, so it won't make very heavy elements. Once our star, or any star, runs out of fuel, that means there's no more explosions on the inside trying to keep the star up, right? Because remember we said it was balanced. The explosions and the gravity were balancing each other out. Once the star runs out of fuel for the nuclear explosions, once it runs out of fuel, it can't explode, which means gravity will then completely squeeze the star as hard as it can. And the star can't really do anything about that. That's why we see here the star can collapse. Here's kind of what's going to happen to our star. When a sun-sized star convert the hydrogen in their cores to helium, fusion takes place outside their cores and they expand to become red giants. So when our sun gets close to being dead, it's going to start using its secondary fuel. And because it does that, the reactions go a little faster, gets a little hotter, and the sun will expand to this size. Right now it's this big. When it goes through this and becomes a red giant, it will be this big, meaning Mercury will be completely engulfed by the sun. And the Earth will be a lot closer to the sun. All right. So this is essentially a star giving its last try, right? Putting in the last bit of effort it can. It's almost out of fuel, so what is it going to do? It's just going to use anything that it has as fast as it can to make sure it stays alive, and as it does that, it expands really big. But that can only last for so long because it can run out of fuel during that red giant stage. We see here white dwarfs are formed by red giant stars that lose mass from their surfaces until only their core remains. They are small and emit white light. So once this gigantic red giant runs out of fuel, eventually chunks of the star just kind of fly off into space, and all that's left is the core. When our sun does this in a couple billion years, what will be left is the core of the sun, but it'll be pretty small. You see here, this white dwarf star is as big as the Earth, but it weighs as much as the sun. So if you took all the material in the sun and squished it down into the size of Earth, that's kind of what a white dwarf kind of looks like. They're really strange, and they break even more rules that we're not going to get into, but if you're interested in that, you should take astronomy next year, because we go over this a lot. But they're small and they emit white light. So our sun will end its life being a white dwarf. And then once it becomes a white dwarf, it is really hot, but it never actually makes any more energy. It's just really hot, and then eventually will get really dim until it no longer has really any heat giving off anymore. But that hasn't happened yet. Oops. But it's possible that a star never gets to slowly die like that. Instead, when a supergiant star explodes, it's called a supernova. And during a supernova, temperatures in the outer layers of the explosion are high enough to produce all of the elements heavier than iron through nuclear fusion. What that means is the explosion is so massive that atoms are combining that probably shouldn't be combining and making elements all over the place. So all of the elements on the periodic table are formed by these supernovas, essentially. So in supergiant stars, the core runs out of fuel. All of the material squishes the core as hard as it can. Squishes it so hard that it turns everything into neutrons. So remember, we talked about electrons, protons, and neutrons earlier in the year. These supermassive, supergiant stars can squish each other so hard that there's no more protons and electrons and neutrons. Everything just squishes into neutrons. And when it does that, it becomes this super dense neutron star that doesn't really like to get squished. So as this material keeps squishing, the neutron star keeps bouncing off all this material. And you can imagine bouncing off all this material means as it goes down, it bounces off this and flies off out into the world, and that's how we get the explosion happening. The core of one of these stars is called a neutron star. Extremely dense. Right? So the other picture we saw, it had a ball like this compared to Earth. Notice how this ball is compared to just the city of Manhattan. This ball is 1.5 times the weight of our sun. And it squeezes into such a small area that it's barely bigger than Manhattan. Okay? So this is a crazy, crazy thing. Again, breaks a lot of rules. If you're interested, take astronomy next year. It's composed of pretty much neutrons. Each teaspoon or tablespoon weighs like millions of pounds. It's insane. Now, if that star is big enough, what happens is when the neutron star gets squished, it gets squished so hard that it makes a black hole. And what that is all the material gets squished so hard that gravity is so strong that it just squishes down everything again into nothing. All of that matter, all of this 1.5 weight of the sun is squished into nothing, and that nothing makes a gravitational pull so strong that it can pull in light. And once you pass a certain point near the black hole, there's nothing you can do to get out. Light can't even escape. You say, well, what if you were inside the black hole and turned like on a lamp or like a flashlight and shine out? The gravity is so strong that the light can't even make it out. That's how strong the gravity is. Now, we can't actually see black holes, so some people say, well, how do you know they exist? The only reason why we know they exist is because there's a lot of stars that actually orbit each other. And what happens is one of these stars will become a black hole and the other one isn't. But what we can see is that this star is just like all of its material is getting sucked away into this weird spot that's giving off a bunch of radiation, but we can't actually see it. And remember, we can't see it because it's a black hole. Light can't escape from it. So our telescopes, all that stuff is based off of being able to see things. So if we point a telescope at a black hole, we're not going to see anything because there's no light from it to show us. But instead, right on the edge of the black hole, there's a lot of radiation that we can see. And if it's by one of these stars, like we just said, we can see the material going right there and then kind of disappearing. So that's how we think we know, or that's how we know where black holes are. Here, I think within the last 2 years, we took our first picture of the black hole, and this is kind of what one looks like. The center is obviously black because you can't see it, and all this red stuff, all this orange stuff on the outside, I don't know why I said red, all this orange stuff on the outside is radiation. And here's a little chart, a handy chart that tells you kind of everything that can happen. From a star-forming nebula, we can go one of two routes. We can make a sun-like star, or we can make a massive star. So let's look at the sun-like star, because that's the one we're most common with. It becomes a protostar, which remember, it's just hot because it's squeezing itself so hard. Eventually, nuclear fusion happens, so it becomes a sun-like star. And our sun goes along for billions of years. Eventually, it almost runs out of fuel, so it kicks in its secondary fuel source. And because of that, everything's burning super fast, so the inside pressure gets really big, and we get a red giant. Over time, this red giant shoots off pieces of itself because it's running out of fuel. And we get something called a planetary nebula. We didn't talk about that, but that's what it looks like at that point. The very middle of the planetary nebula will be called the white dwarf, because that was the core of this star. And all that gas and dust will go up into space to maybe become another star-forming nebula. So like the stars get recycled. If we look over here, on the other side, we have a star-forming nebula, and just like last time, we have enough stuff that this protostar is getting heated up because it's squishing itself so hard. Well, after it squishes itself hard enough, nuclear fusion happens, and it becomes one of these massive stars. Notice how these massive stars only last millions of years instead of billions of years. So this massive star goes throughout its life for millions of years, kicks in its secondary fuel source, becomes a red supergiant instead of a red giant. And this one doesn't get to have a peaceful end like this planetary nebula. Instead, it goes supernova and explodes. There's so much mass that it has to explode. Now, all the gas that it shoots off gets to go back into being a nebula. But the core can either become a neutron star or a black hole. If it's really, 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 really big, it becomes a black hole. If it's just really, really big, it becomes a neutron star. And that is it for lesson 2.